Well, good evening everybody. Welcome to this meeting of the West of London Astronomical Society. And if there are any new or prospective members here, that's a bit of light, it's nice, then welcome to you, and if you want to know anything about the Society or indeed about astronomy, just ask and we will be happy to tell you what we know. I'm very delighted to say that our speaker tonight is Professor Giovanna Tinetti from University College London. She is head of group of astrophysics at UCL. She also has a post at the Harwell, I forget the name of the group, but you've got a connection there. And she is going to be the principal investigator. She is the principal investigator of a brand new satellite which is going to jostle for space with the JWST at the Lagrange point in a few years' time, looking for atmospheres of exoplanets, and that is the subject of what she's going to be talking about. She's given us an exciting title, A Remote Journey to the Planets of Our Galaxy. And I was just saying, she's never going to run out of material at this rate. So I last heard her speak in 2017, and she's assured me that the complete different talk, because there are different planets, new results, and I think probably in another 5 years, completely different planets yet again. So over to Giovanna Tinetti. Thank you.
Good evening to everybody. It's a great pleasure and a great honor for me to be here tonight. So thanks for this great invitation. Can you hear me well? Or should I?
Yeah, there's a... I can turn it up if not.
Is that okay? Yeah. Perfect. So let me just start by saying that what we discovered in the last more than 20 years or so is that planets are really ubiquitous. And so, statistically speaking, we're expecting to have at least as many planets as stars in our galaxy alone, the Milky Way. But then, of course, why our galaxy should be different to any other galaxies in the universe. So, if the stars in our galaxy are billions and billions, then you do the maths and you work out how many planets we should have in the universe, given that there are billions and billions of galaxies in the universe. So we're expecting all these planets, but as I said, it's a statistical estimate. And actually today we don't know yet all these billions and billions of planets. What we know, we have about 5,000 or so confirmed exoplanets. So for exoplanets, I mean planets orbiting other stars, the stars that are different from our own sun. And these are confirmed because they have been detected throughout the years with a number of techniques. Tonight I'm focusing more on the understanding the characteristics of these planets, so I'm not going to talk about what kind of techniques we're using today to discover new planets, but of course if you have any questions then I will be more than happy to answer. But what is quite extraordinary is that most of these planets we know being organized in planetary systems, so not necessarily just one star and a planet, many organized in planetary systems, a little bit like our own. But there are of course many stars that do not have planets at all, and there are stars on the contrary that are sort of shared by one or multiple planets. So we have many planets being discovered around binary stars, for instance. So there are all sorts of combination of star and planet system. And we already start to have some exomoon candidates. Candidates because we're not really sure what some of these exomoons that have been potentially detected so far, but it really shows how far this field has gone. Now, what I personally think that is quite revolutionary of this field is not even the number of planets being discovered during the past decades, is the variety and diversity of the planets and the stars that are hosting these planets. And I'm showing you here two plots. In the plots on the left, you look in basically all these colorful dots are all planets, are all exoplanets, so all planets around our stars. You can see in the same plot the symbols of the planets in our own solar system, and these colorful dots, which are exoplanets, are plotted against their separation to their star, their same major axis in astronomical units, and I'm sure you know that one astronomical unit is the distance between the Earth and the Sun. And in the y-axis we have the planetary radii in units of Earth radii. So as you can see straight away, all these colorful dots are telling us a story which is very different from the story that we're seeing in our own solar system. We have many planets orbiting very close to the stars, but more in general, they are sort of covering this parameter space in a much more continuous way than the solar system planets, which are a little bit more sparse. And actually, most of the empty areas that you're seeing here are not necessarily because no exoplanets do exist in those areas, but we believe they're still linked to the observational biases that we still have with many of the methods that today we're using to discover new planets. So in a few years' time, I think this plot, this diagram, will full of colorful dots. It's still not complete because of the difficulties we still have with current instrumentation. If you look at the plot on your right, again, that's another example to show how diverse, how different are the planets around our stars. Here we're looking at exoplanets, again, the color dots, measured against the separation from the star in your x-axis, and in your y-axis you have the orbital eccentricity. Now, most planets in your solar system are orbiting in a fairly circular orbit, but however, we're seeing planets in very eccentric orbits, and sometimes the eccentricity go up to 0.9 even more, which is more similar to what we're used to in the solar system for comets. But over there, most of these planets seem to have this sort of eccentricity. So these are just some example of the variety of situations we are seeing out there. So the real question that we have today in astrophysics is why we're seeing all this diversity, why the solar system is not really the sort of standard model of planetary system in our galaxy. Before discovering all these planets, we thought the solar system is the example of planetary system. But it's no longer the case, and so we won't really to understand why. Now, another thing that really surprised us quite a bit is that, statistically speaking again, we believe that small planets are more common out there compared to big planets like our Jupiter, our Saturn, or even intermediate sort of planet like Neptune or Uranus. And this statistics is coming out of Kepler. Kepler was a NASA mission that was launched in 2009, retired in 2018, and currently we have TESS, which is basically doing part of the work of Kepler. There are some differences. And both TESS and Kepler, but also our techniques from the ground, are indicating very strongly this bias where the small planets seems to be more common. Now, we still are a little bit more biased towards planets that are orbiting relatively close to the star, and so the statistics for the moment, the one that you're seeing here, is still connecting to planets with orbital period of less than 100 days. And so things might be slightly different if you are slightly far away from the star. But still, we have also some evidence through the microlensing technique that this might be the case. And so bottom line, as you see this sort of bimodal distribution, well, first of all, this distribution is telling us the small planets, for small I mean in between the size of the Earth and the size of Neptune. These planets are much more common compared to, as I said before, to Jupiter or Neptune-like. But also we are seeing these two bumps and these two peaks. And one peak seems to point at planets similar to the Earth in terms of size, but the other peak is pointing at planets that we have no idea exactly what they are because they don't exist in our own solar system. They seem to be in between, again, the size of the Earth and the size of Neptune. We know very little about those because, again, they don't exist in our solar system. So something else that we're learning out of different type of observations is coming from ground-based observations, in particular using ALMA. So what you're looking at in the images on your left are a structure of disks. Protoplanetary disks are basically the nursery of planets. These are structure where planets are forming, and typically they are disks of gas, mainly molecular hydrogen, but also dust, typically 1% compared to the gas. And these are basically the structure. At the center of disks, protoplanetary disks, you typically have the protostar, so the young star that is forming. And what has been really, really quite puzzling was for the first time seeing the incredible structures that these disks have. We were expecting something much more plain and regular, but actually these disks seem to show all sorts of structure. There are rings, there are spirals, and they're very diverse one from the other, which again means that perhaps some of the diversity that we're seeing in planets ultimately might come from this diversity that we're seeing in disks. It's early days, we still haven't really made the full connection between how exactly planets are forming in disks. Of course, there are many theories, but there's still many open questions. But what is also quite extraordinary is that in the meantime, we're getting more and more observations from the body in the solar system. And in particular, what you're looking at in the plot on your right is just an example of the kind of isotopic ratios that are currently being measured in meteorites, but also in other bodies in the solar system. And so these isotopic ratios are telling us the story of the solar system, many bodies in the solar system. And in order to understand this mosaic, what happened, somehow we need to connect what we know about exoplanets and what we're getting out of these measurements in the solar system. And both they're telling us something very strong, that giant planets like Jupiter needs to form very fast in these protoplanetary disks, much faster than what we thought was the case years ago. Because otherwise the gas is gone, and given that giant planets like Jupiter need a lot of gas in order to be able to form, they typically have to form in less than 1 million years, which is super rapid, way too rapid for models. And so there is an entire new generation of models of planet formation that are being revisited, because otherwise we cannot cope with this sort of clock that we're getting out of the solar system or out of these protoplanetary disks. And so this is just an example. There are many, many more. And so we have all these new questions that we want to be able to answer in the next decade. Why the solar system is as it is? We started thinking we were the center of the universe, quoted and quoted. Our solar system was the paradigm. And all of a sudden, guess what? Not only we're not the center, it looks like we're not even really very similar to many other systems out there. And so all of a sudden, we want to understand why. We want to understand the chemistry of exoplanets, not only because we're curious about this chemistry, but also because I showed you before these fantastic structures that are coming out of ALMA. Now, ALMA, on top of showing us this structure of the dust and of the gas, is also giving us a very precise information about the chemistry of these disks. And the chemistry is really, really very complex. It's very local. And again, going back to trying to explain some of the diversity we're seeing in this exoplanet, this chemistry might help us understanding what's going on. And so we want to understand what exoplanets are made of. Well, of course, we want to know about the atmosphere and the weather, but mainly we don't know whether it's so diverse, why the solar system is as it is. We think this diversity might come from formation, might come from the evolution, meaning the history of these planets, but what is exactly happening we still need to understand. And of course we're interested about the visibility, why not? So what do we know right now about this 5,000 plus of exosolar planets being discovered? Most of the time very little. For most of these planets, well, for a good fraction we know how big they are. We know how much they weigh, so we can measure the mass with some other techniques. And we typically know also how far away are these planets from the star. And so out of the distance between the star and the planet, we can, at zero order, estimate a temperature, but this is just an estimate. And so out of this information, we start to draw plots like this. We put the mass of the planet, the radius of the planet in the x-axis, and basically what we're looking at is the density of these planets. And if you look at a relatively simple diagram like this, you will see that the giant planets like Jupiter and Saturn are clustering up here. Then you have, this is the Earth, and so we don't have so many planets as small as the Earth yet. And then you have all a variety of cases around here. And so if you know the density of an object, at zero order you can try to figure out what is the composition of that object. For instance, we know that a planet like the Earth is rocky, so rocks are very dense. We're talking about a density of roughly 5.5 gram per centimeter cube. And so ideally, if we know that if a planet has a similar density, we are expecting that planet to be more rocky type. Giant planets tend to be not very dense because they have a lot of gas like hydrogen. And so we know that the density is much lower, 1.2 gram per centimeter cube. And so that's how we are clustering them up there. But actually, there is a variety of situations in between, and if you try to classify a planet only out of a density, you're really running very rapidly into trouble. It's like trying to classify human beings out of the density. We have the density of salty water, but I'm sure you don't want to be classified as salty water. So this is just an example. Planets are much more complex, and so how can we proceed from that? Well, if we're able to measure the chemistry of the atmospheres, and the atmospheres are this gaseous envelope around the planets, then we can really make a huge step forward. And this is because this gaseous envelope is the product basically of the formation of the planet, but also how the planet evolved, the many physical and chemical processes that went through. And so in principle, if we can measure the chemistry, we can also work out which of these chemical and physical processes happened in the history of the planets and why. And of course, if you have only one planet, then it might not be so easy to understand exactly where that molecule may come from. What does it mean having so-and-so component in the atmosphere? But if you start to have tens or hundreds of cases, that's completely different, because all of a sudden you start to work out classes of planets and understand much better what's going on. So in this cartoon here, many physical and chemical processes that might have a strong impact on the chemistry of an atmosphere are being shown. And I don't have too much time to go through this, but this is just to give you some examples. For instance, in particular, in the early phases of the formation of a planet, if you're talking about a rocky planet like the Earth, when this planet is trying to cool down because you have a lot of energy during the formation process, then you also have a lot of volcanic activity. That's how the interior of the planet is basically trying to release some of the energy from the interior. But if you look at the gases that are being emitted through a volcanic activity, well, somehow they are a good window for what is the composition of the interior. And so in principle, if you see certain gases in an atmosphere, if the planet is a rocky type, then that could tell you something about what's contained in the interior. And so this is just an example. There are many others. So this is just to say why we want to understand the chemical composition of all these planets. Now, we are very lucky because since I would say more or less 2005 or so, we start to have a number of techniques that allows us to probe directly the chemical composition of these planets. And it might seem science fiction because probing whether there are some molecules or the temperature of an atmosphere of planets that are tens or hundreds of light years away, it seems to be science fiction, and to a degree, sometimes we still think it is. But actually, we have already many different techniques to do that. And so I just have a few examples of these techniques, but broadly, we have the transit technique, the one that is shown on the left. So for this technique, we are relying on the fact that at a certain point the planet is passing in front of the star, we call it transit, or going behind the star. And so if we are in this sort of geometry, then you can really play out the position of the planet with respect to the star to play tricks, subtracting out the star from the star plus planet, adding, so you can always separate the two measurements depending where the planet is with respect to the star, but you need to have the specific geometry. The transit technique has been extremely successful, not only to find new planets. Kepler tests have been using this technique to discover really hundreds, even thousands of new planets, but also to get into the atmosphere. And so I will show you a few examples of this. But then you have a complementary technique which is called direct imaging. In this case, what you're doing, what you're looking at here, this is where the star is. And the reason why you're seeing a spot instead of a star is because the coronagraph has been used to mask out the light from the star. And what you're seeing here is really an image of the planet. So this is not an artist's view, it's a proper photograph of your planet, which is quite mind-blowing. And so in principle also here you can detect the planet with this technique, but you can also study the composition of the atmosphere, similarly to the transit. And the way you do this, whether it's transit or whether it's direct imaging, what we're doing, we are basically splitting the light into wavelengths. So instead of collecting all the light in your detector, if you have a spectrograph, then you can basically detect the planet on multiple wavelengths. And by doing that, then we can work out what is the chemical composition in the atmosphere. And the way we can do that is because molecules are all absorbing light in a unique way. And in particular, in the infrared, they all have very different spectral signatures. And so if you know what is the spectral signature of each of the molecules, then you can always compare the spectral signature of the molecules that you have from lab measurements or your calculations to the real observations and work out basically which molecule can match your observations. We can also do spectroscopy from the ground, and from the ground you typically use very high resolution spectrographs because you want to be able to separate the contribution of the Earth atmosphere from the atmosphere that are very far away. And so today also this technique is becoming very popular. All these techniques are all very complementary. They are typically looking at slightly different type of planets, and they also probe different parts of the atmosphere. So they're not necessarily in competition. You really want to use all of them if you can. So just to give you an example of some of these techniques, this is a planet that has been detected through direct imaging. So you see the planet being detected here, and here is where the star is. If you split the light into wavelengths, then you get something like this. And then, as I mentioned before, if you compare these observations with the signatures of molecules, then you can work out which molecule could cause that bump or that absorption. And not always, but in principle, you can work out what is the composition of the atmosphere. This is another example, this time in transit. Also in this particular case, the observed spectrum is in black. Now, with transit, in particular from space, using telescope like Hubble or Spitzer, we were able roughly to look at 80 Jupiter type or Neptune type of planets so far, which is not a small number given the fact that these are relatively difficult observations. When I say difficult, it means that you need to try to get precision or 10 or 100 part per million, so it's really precise type of measurements. But even current instrumentation can already do that, which is not bad at all. It's not perfect, and so it was with great relief that we have seen the James Webb Space Telescope being launched some time ago. And luckily, this telescope, that is the biggest ever being launched in space, we're talking about a 6.5 meters diameter telescope, launched in L2, which is 1.5 million kilometers away. So there were a lot of things that could go wrong, but luckily they didn't. And so the observatory is working very well. And what you're seeing here is one of the first observations that we're taking of one of these exoplanets out there. So for the moment, they are not yet a huge discovery that we haven't really thought of before, but more and more the new observations that are coming out, and so very soon there will be probably some great discoveries, because clearly James Webb is much more sensitive and has a much broader opportunity really to probe in the spectrum, and so we're expecting great things out of it. Another thing that we're doing sometimes is not only to look at a planet in one specific moment in time during the orbit, but in some cases, in particular for planets that are orbiting very close to the star, and so they complete an entire orbital period, sometimes in less than 1 day, we can afford to follow the planet around the orbit. And so in some cases this has been done, and when that is the case, then we can work out what is the thermal profile in the atmosphere, but also how the spectrum is changing depending in which part of the orbit the planet is in. Now, I talked quite a lot about giant planets so far, but we are already getting quite close to be able to look at smaller planets. So the famous super Earths that I was talking about before, these objects that we know very little about. And one of the first super Earths that have been probed with Hubble is this K218b. We're talking about a planet that is roughly twice the size of the Earth, and is about 8 Earth masses, something like that. And so we still don't know so much about this planet, but Hubble has identified in 2018, these are the data that were analyzed by my team at UCL, we have seen that the data out of Hubble are suggesting of the presence of water vapor in the atmosphere. There's probably not only water vapor, probably there's still some hydrogen, because otherwise we wouldn't explain some relatively strong signal. But this is an interesting super Earth also because the temperature of this planet is roughly the temperature of the Earth. Does it mean this is habitable? No, I'm not suggesting that. We only know for the moment that the temperature is certainly a good one, if you're interested in habitability. There is water vapor in the atmosphere, but we still don't know exactly what is the nature of this planet. It could be a small Neptune, it could be what we call in jargon an ocean world. This is just based on the density of these objects. Ocean worlds are basically worlds where we believe there is a very thick ocean either at the surface or beneath the surface. Again, we know very little about them, and so this could be an example, but as I said, we still need to know much more. I mentioned of the James Webb possibility to look in particular at some of the small planets, and where certainly James Webb will have a big contribution is in looking into small planets around stars that are colder and also fainter than the Sun, what we call in jargon M-dwarfs. And this is because for M-dwarfs, if you're interested in particular in habitable worlds, since an M-dwarf is colder than our own Sun, then the area around the star where the temperature is right to have liquid water is much closer to the star. And if that is the case, it means that we can probe in an easier way some of these planets using transit. And so that's why we're quite interested with James Webb to look in particular about some of these super Earth around M dwarfs. In the meantime, I'm talking about Hubble, many techniques. With some colleagues at UCL some years ago, we have founded a company called Blue Sky Space. And clearly we're not trying to compete with these big facilities, not at all. But what we're trying to do is to launch regularly some small satellites in order to complement and help and support some of these big facilities. And so we have been working for a number of years now about the Twinkle satellites that will be built by Airbus and ABB. But we have a second smaller satellite that will be launched next year. It's called MOVE. And MOVE is a small satellite that will look more in the UV part of the spectrum. And the idea we want to is to use MOVE really to look at some of the flaring activity that in particular these M dwarfs might have. And in particular, if you're interested in visibility, understanding what the star is doing and whether or not it's a very active star, it can be very valuable. If we're looking at what will happen very soon, so we already talked about James Webb. In a few years' time, the Plato mission from the European Space Agency will be launched, and Plato, a little bit like TESS and Kepler, will discover new planets, and in particular, Plato will focus mainly on small planets, cold, and so really pushing more towards the habitable zone. In the US, the Roman Space Telescope will be launched, and Roman will help, in particular, to detect new planets with direct imaging. And a unique contribution will be mainly to look at relatively cold Jupiters, not just warm Jupiters like we have so far. And later on, I want to spend a few words, if that's okay with you, about Ariel. I'm particularly attached to Ariel because I really want to see it flying, because Ariel was adopted by the European Space Agency in 2020 to be the next medium-sized mission to be launched, and we're talking about a launch in 2029. So what is Ariel exactly? So Ariel, like James Webb, will be launched in L2, so 1.5 million kilometers away from the Earth, together with another mission that is also extremely interesting, Comet Interceptor. And so these two satellites will be launched there. Ariel is a 1-meter class telescope, and the unique selling point of Ariel, in a certain sense, is the ability to do spectroscopy from the visible down to the infrared in just one shot. And this is something excellent if you want to do atmospheric characterization of exoplanets, because you don't have to use many instruments in order to cover this waving range. James Webb is wonderful, but even James Webb, if they want to cover a broad waving range, they have to use their multiple instruments one at a time. And in the case of Ariel, we can do everything in one shot. The idea is to select more or less 1,000 exoplanets, because we want to follow up and look at the atmospheres. So not really discover new planets, but really more to characterize the planets that are already known. And among these 1,000 or so, we want to select some rocky type, some gaseous type, very hot, very cold, around different type of stars. And so really have the big picture of how the exoplanets in our galaxy are made of, and what they are really, because today we don't really know. The Aerial Consortium at the moment is including around 500 scientists and engineers from 16 ESA countries, but Ariel is UK-led. And so we have also the contribution of NASA and also JAXA, which is the Japanese Space Agency. So I mentioned this UK-led because Ariel will be assembled, tested and verified in Didcot at Harwell in a big chamber. You can see the picture here at RAL space. And then basically when the entire payload is tested and integrated at RAL, it will be sent to Airbus Toulouse, and it will be basically integrated to the spacecraft that you can see here. So I mentioned that we have this broad web and coverage between the visible and the infrared in terms of spectroscopy, and this is because we want to make sure we're able to discover all this list of molecules and many more, but also measure the temperature, given that we're observing in the infrared, and simultaneously we can also use this information to work out whether there are some clouds, what is the effect of the star, and many other things. So we'll really be able to extract a lot of information out of these planets. Now, we already have a long list of target candidates, and very soon this website that you're seeing here that has been done by Hamed Arifai and UCL will become public, and basically anybody will be able to have a look at the performance that Ariel can have on each of the planets, and even vote for the planets that Ariel should observe during the lifetime of the mission. So anybody will be able to, not just scientists, to vote for that. We have in the same website, there is a simulator of the aerial performance, and so anybody really interested to understand whether their favorite planet can be observed by Ariel and how long does it take, you can use the simulator and see exactly what's happening. And so again, if any of you is interested in that, then this website will be available very soon. But in the meantime, we're also engaging with the broader community in many other ways, and I have just two examples that I want to show today. One is the area of the challenges. So of course, you're aware that AI is everywhere at the moment in the modern society, and we want to make sure that AI is helping us in a good way in order to analyze the data of Ariel in a very efficient way. And of course we have many AI experts in the team, but the best way actually to make sure that we're indeed using the best AI techniques is to have every year some data challenges. And so we already had 3 at this point, 2019 and 2021 data challenges were basically asking the machine learning community to help us finding out best techniques to correct for stellar activity and some of the instrument systematics, and the result has been fabulous. In particular, one of the winner is a machine learning expert, Luis Simões in Portugal, and he became quite famous, so famous that he appeared even in a TV show in Portugal. So clearly this was quite unexpected. And the Aerial Challenge 2022 was hosted by NeurIPS, which is one of the most prestigious conferences of machine learning in the world, is where Amazon and Google typically have their discovery challenges. And so also here at one of the data challenge here, and it was a massive success. So we had over 200 participants from more than 39 countries around the world, and so clearly we want to keep doing these data challenges because we're learning really quite a lot, and we have the 2023 one that will be launched very soon. So if in the audience there is any of you interested in participating and competing, because we always have some awards and prizes, then the one in 2023 will be out very soon. In this month, so you can wait for that. I also want to make sure that it's clear that not just space is great in order to look at atmospheric composition, also from the ground you can do quite a lot, and in particular it's quite complementary what you can do from the ground compared to space. From space, you can observe very well, you have a very good visibility of the sky, In the case of Ariel, for instance, you have full coverage of the sky throughout the year from L2, and the simultaneous field of regard is typically, well, it's 100% in more towards the polar galactic region, and drops to 40% closer to the ecliptic. But you still have great visibility. Of course, from the ground you have less visibility, but from the ground you can certainly have even bigger facilities compared to space, and then it means that you can always have much higher spectral resolution, and this is something that is hard to have in space. And so clearly you want to use facilities from the ground and space in a complementary and synergistic way. My last point before wrapping up to conclusion and get your questions is about the Exolog project. Now, Exolog has started as part of Ariel because we identified early on with the mission that actually, since we're aiming at 1,000 targets or so, for many of the exoplanets that are currently in the list of target candidates, we don't know so well the ephemerides. And if you don't know very well the ephemerides, it means that you might point your telescope when the time is up to the wrong moment to that specific star, and basically lose your transit and lose time of the mission, which is certainly not what you want to do, because it's fixable, but it means that you're wasting telescope time, and telescope time is very precious. And so Anastasia Kokori and Angelos Tiaras, both of them were at UCL when they started this. They started this big project asking for the help of all amateur astronomers around the world, not just professional, to help us following up basically these hundreds of targets for which we don't know the ephemerides so well. And what it was supposed to be a relatively focused and small project, it became an enormous global success. So now Exolog, I'm pleased to say, is including more than 800 participants, 50 countries, you see in the diagram there. 77% of the participants are Exolog amateur astronomers, and it has been an enormous success because now we have ephemerides for about over almost 500 planets, and most of these discoveries and this refinement ephemerides have been published in a number of extremely high impact papers like the Astrophysical Journal supplement series. It's super hard to publish in these papers, and as co-authors you have 200 and more people, are all the people who helped observing. And so this has been a massive success. So again, if you're interested in helping, we would welcome your help, because we really need to have more ephemerides, and there are some new pilot studies as part of Exolog to again ask help to refine some of the characteristics of the host stars and some other planetary parameters. So again, we're really relying on this work. Okay, I'm conscious of time, and I certainly want to have time to answer to your questions if you have any. And so let me wrap up to conclusions here. We have discovered during the past 20 plus years that planets are ubiquitous in our galaxy. We still know relatively little about them. The good news is that, first of all, in terms of completing the census, the demographic of planets, we have really a long list of satellites that are currently operating or will be launched very soon. I'm citing in particular test cubes and Plato, but also Gaia, as should be mentioned, and there are many more other facilities from the ground. When it comes to understanding the atmospheric composition, then again we have facilities, general facilities from the ground, like the extremely large telescopes, but also satellites from space. In particular, I mentioned James Webb, in a smaller scale Twinkle, and also Nancy Roman. And this will be certainly great in starting to understand the composition of many more planets compared to what we currently know. But I think Ariel will give us really the first opportunity, being a dedicated mission. That's where we can go for the large scale sample, really big statistics. And at that point, I think we will really know how diverse, how different to each other are all these atmospheres, and out of these many planets being looked at and observed, we'll be able really to understand what is the main sort of, where there are many classes of planets in the galaxy, how they look like, and so on and so forth. Something that we don't really know very well so far. And so before concluding, just as a reminder, although some of these planets are relatively close by, they're not really so close by. And so I think we don't think we have the chance for the moment to go there. And so just a reminder to all of us that we need to take care of this one, because for the moment we don't have a plan B. Thank you very much for your attention.
Can we have some lights, please? Thank you. Well, that was very exciting, and I was particularly interested to hear that amateurs could play a part in the search for exoplanets, and perhaps I could start off by asking what equipment one would need to do that.
Excellent question. If you go to the exolog.space website, they are very organized, and so they put all the priorities of the targets with depending. So you can include the information on your equipment, where you are, when you want to observe, and you have all the priorities, so what you can observe, what is visible, and then they have also all the tools to analyze the data, or for you to analyze your data, and so it's all extremely well captured on the website. And then normally they have a number of workshops, and typically they do it at least once a year in the UK, typically in London, because it's very convenient. Last year it was in September, and my understanding this year they want to plan something in October. So that's another way also to.
So probably we're talking about transit observations, aren't we?
Yes.
Yes. Which I'm surprised to find that, and I know that one of our members has got one of these EV scopes, which is just a tiny little telescope, and brought it along. He takes pictures from the car parks here, and people observe using quite a small telescope these exoplanet transits.
It's still okay, because at the end of the day, a Jupiter around a sun-like star is 1% of light drop. So normally you can do that with relatively small equipment.
A few people in the BAA have been doing that. I gave some awards out to them, really, from around 6-inch to 12-inch aperture with CCD cameras. There seems to be a lot of targets in range of even rather small telescopes.
So quite small instruments, 6 to 12 inches, and CTD cameras. It always intrigues me whenever I take a picture and you see, just in a few seconds exposure, you see 20, 30, 50, 100 stars, and you think, well, there's just stars. What's there? On one photograph you can't tell anything about it, but over a period of time, then one of them might just have an exoplanet transit across it, and it would dim. So there's a lot of potential there. Any questions now? Yes, over there.
So I wanted to ask, what do you believe is the most promising candidate, promising exoplanet candidate for life right now?
That's an excellent question. So I think we are all very interested to see what's happening in the TRAPPIST-1 system. So TRAPPIST-1 system is a system where you have 7 planets in between the size of the Earth and the size of Mars, around a star that is much colder and smaller than our own sun. It's called TRAPPIST-1 because this system was discovered by a group in Belgium, and so they took the name out of the beer. But this system is very interesting because it's very compact. Most of these planets are, 7 planets are transiting, and they are, some of them are in the so-called habitable zone, and being small, potentially habitable zone has attracted a lot of attention. So James Webb is doing tons of observation for the moment of the system, so we'll know something about some of those planets probably very soon. I'm very interested about this K218b, not necessarily because of its visibility, it's because I think it's an interesting word. But the list of super-Earths that can be observed is getting longer and longer. And so, although we all started with our own favorite pet planet. Now the list is so long that I'm not entirely sure we should really just go with the favorite one. And so I hope we will know much more about these planets very soon.
But how about that so many planets orbiting Dwarfs one, I believe, are tightly locked to a star? So you could have an interesting situation where on one side of the planet it's a scorched hellscape, on the other side it's a frozen ice world, and perhaps there's some habitable zone on the planet on the prime meridian, so a very small, narrow strip that's habitable. That'd be a very interesting world to see, I think.
Well, of course you're right, and there has been some article in the literature suggesting that again one should stay again in this sort of band on the planet in the area that is not too hot and not too warm. At the same time, if you have an atmosphere and you're not tightly locked, then perhaps the situation is slightly simpler. So among the many planets that we'll be able to observe, hopefully there will be some of those that are slightly less complicated if we're interested in habitability. But thank you so much. That's all great questions.
Question over here.
I think they just announced TRAPPIST-1b has no atmosphere in the last day or so.
It is, well, it's one of the first observations after James Webb, and again, we're early days. The zero order seems to suggest that there is no atmosphere, or a thin one. Again, is the start, I would say. And so I think you certainly want to repeat that measurement and other measurements at different wavelengths to make really sure that you really don't have an atmosphere or you have a thin one. What I'm trying to say here is that it's just starting the entire business.
There's quite a lot of planets to go there.
Yes.
Paul.
Yeah. A fairly basic question, and I think you did address it to some degree. It just concerns the atypical nature of the solar system. As you said, the eccentricity of exoplanets is very different to the eccentricity of solar system objects. Can you indicate, what are some of the factors that might be responsible for the atypical nature of the solar system?
Yes, so we don't know, I should perhaps say that we don't know whether the solar system is atypical. It's certainly not the typical or the standard model of planetary system. I don't think we have a complete statistic yet to say the solar system is rare. It's a step that for the moment we cannot really take. But certainly a planetary system like the solar system is suggestive of planets that are formed in this disk, because most of them are rotating more or less in the same sense of the rotation of the star, with a couple of exceptions. And they're all in on the same plane, and again, most of their orbits are almost circular. So it's all suggesting that they're all formed in the disk, and somehow in the disk the number of dramatic events perhaps was not as high as in other places. When you start to see planets that, on the contrary, are perhaps with a high ubiquity in the orbit, or very eccentric orbit, or they have a retrograde sort of orbit, that is probably indicative of collisions or some form of gravitational interaction with other bodies when the gas is gone in the disks. And so it's probably indicative of a history that has been a bit more dramatic. And of course, for the moment, our statistics is not large enough and to cover all the parameters to really suggest that is always the case. But it is certainly a fact that many of these planetary systems seem to have evolved in a more dramatic way compared to the solar system.
Okay, thank you very much for that.
Do we actually have any examples of other solar systems which are very similar to our own?
Not really, simply because I think in order to do that, possibly Gaia might be a very good facility. Gaia will be, through the method of astrometry, will be very sensitive to Jupiter types at intermediate distance, like our own Jupiter and Saturn. And for the moment, with radial velocity and transit, it's quite impractical to, you see very well hot Jupiters, planets that are orbiting close closer to the star, but not necessarily intermediate distance. And so I think Gaia will be able to identify systems where the giant planets are more or less at the same distance than ours. And then you will need to also then to discover somehow the smaller planet inside, and if they're not transiting, it might be a little bit tricky. So what I'm trying to say here is we don't have yet an exact copycat to the solar system, but I think it's more an observational bias than anything else.
Yes.
And so in a few years' time, we should know whether or not we have any more system more similar to ours.
Yes, on one of your first graphs you showed quite a cut-off
Yeah.
at the size of the Earth, didn't you? So that does imply.
The intermediate distance is really tricky because we have direct imaging that is probably in very large distances, or microlensing, and then you have a gap, intermediate distance, and then you have the transit radial velocity, which is the planets closer to the star. But in between, we're still missing some data.
Yes. Okay, the question here, yes.
With hot Jupiters, how is it possible for these planets to keep their atmospheres, or is it just a timing issue and they will eventually all disappear?
So, first of all, when they were discovered, the first planet discovered, the Nobel Prize to Major and Queloz because of the discovery of 51 PEG-B, it was very puzzling because most of theoreticians thought that you can't really have giant planets very close to the star because they should fall a larger distance where most of the gas and dust is in the disk. But then what it was understood is that yes, they do form there, but then they tend to migrate inward, in particular while you still have gas in the disk, because it's like the disk is sort of dragging this planet closer to the star. Now, if the gas is gone before the planet is basically disappearing on the star, and so the planet stays where it is, where we find it, which is relatively close distance. Many of these planets, you're right, they are orbiting so close to the star that one starts to wonder how long they might exist in these conditions. And it is true that in the ultraviolet, particularly with Hubble, it was discovered that many of these hot Jupiters seems to basically have relatively unstable atmospheres. They have atmosphere at the top that are in so-called hydrodynamic escape. So basically, hydrogen is escaping very rapidly and is sort of dragging also some heavier element. So imagine like a little bit of a comet with a tail, and apparently some of these planets are exactly like that. Then how long they can exist in those conditions, there are many theoretical calculations, and clearly they are imperfect, because if we leave them, the planet should not be there. So we still have to learn a little bit. But it's just to say that it's true, many of these planets seem to be quite unstable, at least the upper part of the atmosphere seems to be quite unstable.
Yes.
Great, thanks very much for the talk, really enjoyed it. Obviously a really exciting prospect being able to characterise these planets. A lot of them for the first time, really get to know what they have, what their characters are. I was just wondering, how far away are we, do you think, to perhaps characterising exomoons? I mean, I know there's been a couple of candidates and people have been questioning them, but it can't be too long, presumably, before we can actually identify some exomoons. And then given that some of the, Ganymedes, is a very large moon in our solar system, we know that some of them are going to be equivalent in size, really, to planets. Do you think we're a long way off from looking at that? Because obviously moons also have high potential for habitability as well, which also makes them very interesting.
Well, I think that current instrumentation is certainly sensitive to relatively large moons. When I say relatively large moons, it's probably bigger than Ganymede. So, and so maybe that is the sort of, is that threshold that perhaps is not great, because maybe at the end of the day there are not so many really large moons. One of the candidates in the end turned out to be as big as Neptune, and the main planet was as big as Jupiter. So you start to wonder which one is the moon, or is it the binary planets? So the difficulty is, first of all, on the size of the moons, and so the threshold of sensitivity so far, And also, although Kepler has been fantastic in terms of precision, but some of the measurements of Kepler, the timing wasn't really too frequent or frequent enough in order to see some of these small changes that were necessary for exomoons. And unfortunately, Kepler has been one of the most precise missions really ever launched for this kind of work. So I think, okay, James Webb of course could do that, but the time of James Webb is precious, so you can't really go after unless you really have some very good hint. Using it for an expedition to find an exomoon, unlikely. With Ariel, I think almost as an extra product, many people will study the presence of exomoons because we will repeat observation in any case for many of these planets, and so it might come from free. So what I'm trying to say here is, unless at the moment there is something that is particularly favorable, I see probably more the next generation perhaps being able to answer this question a little bit more in depth, simply because facilities are there, but either the timing is not great, or we don't have enough time really to go after some of this. And so altogether came out to the fact that so far we have some candidates, but not really some true discoveries.
It's going to be a while yet by the sound of things, yes.
Sorry?
It's going to be a while yet, I think, by the sound.
Maybe a few years.
Yeah. Thanks.
In the meantime, there are many groups that are actually looking for exomoons, so I hope that, they will be successful.
Any more questions? Yes, have they?
Apart from the philosophical implications, why should we search for habitable life outside of our solar system?
That's a great question, and I certainly started this entire work because I was interested in habitable worlds, like other scientists. And then throughout the journey, I started to be less and less interested in habitability because these planets are interested, in my opinion, are interesting per se, independently whether they're habitable or not. But I think there are still the big questions about life elsewhere in the universe, and I think ultimately it's about also our own life, our own planet. And so I can understand why it's very appealing. You can also understand quite a lot about life on Earth, and therefore, in a certain sense, how we will evolve on this planet, potentially by studying other planets and potentially planets that could host life. So the implication of understanding something that is remote and maybe different from us has always also implication to understand better our own life, our own planet. I don't know if I answer your questions, but I certainly can tell you what I personally find interesting and other colleagues do find interesting, but maybe other people have a different answer.
Okay.
Professor, there was one slide you tried to back out the composition of a planet based on density, right? So I wonder, are there any findings which contradict our understanding between the relationship of certain material and its density on Earth?
Yes, actually, it's very imprecise, and actually it's people that are working in the interior composition that are always putting a lot of caveats. I mean, we do these diagrams at the best that we can do at the moment, but there are many uncertainties, and the certainties to the models are mainly we don't know so well the equation of states of many of these materials, so meaning we don't know so well how even relatively simple materials behave at very high pressure and temperature, and most of the time we don't have enough experiments that are telling us that. And so that is the main problem. So we are sort of extrapolating what we sort of know at our conditions to conditions that are not really applicable, and which we are using this information in an incorrect way, but this is all we can do. Another problem we have is that we don't know the age of the system most of the time. It's very hard to estimate the age of a star and therefore of a planet. And planets, while they're cooling, they tend to contract. And so having their age, it will help us understanding whether they're still contracting or not, and also different temperature, the interior composition might behave in a slightly different way. And most of the time we don't necessarily have a direct measurement of the temperature. In a few cases we do, in other we don't. There are other issues, but I would say the biggest problem is that most of the time one observation can be explained in multiple ways. And so I just give you an example. If you look at the density of silicates planets, like the Earth and Venus and Mars, so the interior is mainly made of silicium and oxygen, silicates. But actually there are many lab experiments that are showing that in principle, if instead of a lot of oxygen you have a lot of carbon, you will form silicon carbide or diamonds in the interior of the planet. But if you look at the density of this particular type of planets, we don't know if they exist, but in principle they could be there. The density is not so dissimilar to the silicates one. So bottom line, if you don't have the composition of the atmosphere, you wouldn't be able to distinguish between the two, and so on and so forth.
David.
Not a question, but I remembered now that I heard a talk, it was at the European Planetary Science Congress, which actually answered the question young gentleman over here was asking about a planet which is tidally locked and maybe has one side really hot and the other side really cold, and they tried to mathematically model this, and they reckoned that it wouldn't be this kind of stable thing that he was imagining. They thought that the atmosphere would be trying to equalise the energy distribution around the planet, so what you would actually get is tremendous hot winds going around the planet all the time, so it probably wouldn't be all that nice a place to.
Well, even in a planet that where you are in an area where you can't go too much further than that is from a habitability perspective is not very sustainable. You need to have a life much more spread. But these are all very interesting modeling sort of issues. I'm sure that when we will be able to observe some of these planets, we will see situations that we haven't really planned or imagined, and so I think the real observation will probably push us to have to debate on things that we haven't really expected so far.
Yes, sir.
Did I hear you use the term binary planet? Could you expand on that?
Well, look, like we have binary stars, meaning that you have basically a couple of stars that are orbiting around each other. In the case of this exomoon candidate, the exomoon candidate was as big as a Neptune, and the planet, the hosting planet, was as big or bigger than Jupiter. Now, when you have a couple of objects that are orbiting each other in that way, I think you're struggling a little bit to find one of the two your moon and the other one the planet. So, I'm saying maybe it's a binary planet just to say that I'm not entirely sure I would classify one of the two as big as Neptune as a satellite. But it's semantic. At the end of the day, if you really have two objects like that, it's just very interesting to see.
Another question again?
Well, this is a question mainly about the definitions of binary planets to expand on this question, which is that, because I know Pluto and Charon are technically orbiting each other, while Pluto mostly dominates orbit, being twice as large as Charon. They still technically orbit around each other in a way. I was wondering what is actually the difference between, as you said, I mean, it's kind of a bit hard to find the difference between moon orbiting a planet and whether or not they're actually orbiting each other. Because even our moon system, the moon actually pulls us, the moon's gravity actually pulls us, so even our planet wobbles a bit around because we're being pulled by the moon. And even Jupiter pulls the sun around. So it seems like everything's in a sort of a binary orbit in a way. It's kind of a bit hard to nail it down.
Are you right? I mean, at the end of the day, these objects are orbiting the central mass of the system. And even the entire definition of planet, dwarf planet, and moons, that was proposed by the IAEA with the International Astronomical Union in 2006. To a degree, can be a little bit arbitrary. For instance, all these planets without stars that have been discovered from Michelangelo, in principle, you cannot call them planets because they're not orbiting a star, and the definition of planet is an object that is orbiting a star. This is just, one example. What I'm trying to say is exosolar planets since the beginning always challenge all these definitions, and so they seem to keep doing that. And so whether we want to, use a definition of current classification to say is this or that, or we want just to embrace the fact that there is this huge variety. That was my point with binary planets as opposed to moon planet. I mean, again, it's a question of definition. In reality, it's just a very interesting object.
If you were a professor on a planet 50 light years away, how much would you be able to tell, and you had JWST and you had Ariel and maybe one or two other things, how much would you be able to tell about Earth? Could you tell that there was life on Earth?
So, just to understand your question, so if I were at 50?
If you were looking back at us,
okay,
and you were trying to detect life on Earth, or just, you were probably, from what I saw, you could tell that there was a planet about Earth size going around this star. What else could you find out about it, given our current state of technology?
What we could say is the temperature, our temperature. We could potentially... Now, the Earth is a tricky one, both for James Webb and also for Ariel. So the Earth, in a certain sense, being so small and so cold and far away, I mean, if you're using transit as a method, it's just one transit every year. So in order to pile up many transit, it's impractical. So, but let's say that you have a better telescope. You might be able to see that you have a lot of oxygen and ozone in the atmosphere that is completely out of equilibrium, and that normally is the reasoning that has been used to suggest that if we look at this equilibrium chemistry and we've seen this equilibrium chemistry on a planet, maybe that is the hint that there is life. Again, maybe, but we had a very interesting debate at the Royal Astronomical Society. It was in January about what we believe today being a solid definition of biosignature and how we can go for it. And I think at the end of the day we were all very all in agreement that although the definition of this equilibrium chemistry to look for life, which is the definition of James Lovelock, for the moment is still the only definition of biosignature that we have. But whether it's robust enough, we don't really know, because many of the atmosphere of exoplanets that we've seen so far, even this very hot JWST, seems to be out of equilibrium. And so the next question is, are we really sure that we'll be able to distinguish the disequilibrium from life, from disequilibrium from our type of chemical network and mechanism that we simply haven't really had the chance of knowing and studying. And we were all a bit cautious about that. And so what we thought that perhaps it could be really useful is to use, again, James Webb, Ariel, whatever we can use in this decade to understand, in particular, non-habitable worlds. Because hopefully, if we understand non-habitable worlds, we'll have a way then to understand a little bit better planets without life, before we might enter into a regime where we're looking a bit more at habitable worlds, and hopefully we will understand a little bit more what's happening.
So turning the tables on us, we might discover more about us in some ways, yes.
But these planets are complex, and so we shouldn't really underestimate interpreting them correctly.
Okay, is that another question?
Yeah, if we got all this excess of oxygen in the outer parts of Earth anyway, wouldn't these beings 50 however far away just say, oh, not more oxygen, we'll have a look somewhere else? Because it isn't a defining factor of life, having an oxygen-rich atmosphere, or is it?
Well, not necessarily. Oxygen alone is not necessarily. What could be interesting is the fact that oxygen, in particular, on an atmosphere like the Earth, is completely out of equilibrium, and so that is what is currently being used as an argument to say that we have life on Earth, because so much oxygen and so much ozone in the Earth's atmosphere is indicative of some processes out of equilibrium. But in principle, you could have other chemical processes that are producing out of equilibrium species, and that was the sort of caution that we all started to have when we have to commit what kind of signature by signature we should look for.
Okay. Well, one last question up there, if I may.
Yeah, I'm just curious about how atypical our solar system is, and reading about how the composition of the solar system, and thanks to the Voyager satellites, how we're learning a bit more about what's immediately just outside of the solar system, and how there's the Oort cloud, and how apparently we are being protected by that big layer in the Milky Way, where we're revolving and everything, and this layer is apparently somewhat protecting us. Has there been any observational, studies done outside here, and were you able to replicate and see that phenomenon, that Oort cloud, that protection in other places?
So just to understand your question, you're talking about whether some objects in the Oort cloud have been
Like the
studied?
solar system and outside the solar system,
Yeah.
those layers and what's protecting us from the further outside of the Milky Way. Is that observational, and were you able to see some similar things in other systems that would kind of replicate what we have in the solar system outside our solar system?
We don't necessarily have so many information about that. Certainly there are other systems that seem to have belts that are similar to our own Kuiper belts. And so suggesting that there are some similar structure more at the boundaries. So there are many systems in particular imaged with ALMA or direct imaging sort of instruments that have shown this for instance, these belts of debris or small bodies like we have a little bit around the solar system. So there seems to be out there as well. So in that sense, there are some similarities.
Thank you.
Okay. Well, I'd like to thank Giovanna
Thank you very much.
And now we hand the microphone over to David Arditi, who is going to explain, well, as it says, observations and sky notes. And thank you very much, Giovanna.
It's only 3 weeks since we last had a meeting, thanks to the bank holiday, and it's been almost continuously raining for those 3 weeks. So you might have thought that we would have very little to show, but that is not the case. In fact, I have a bumper crop of observations to show you. This is partly due to members digging around and getting observations out of their archive from the past that they haven't shown us before. And also, we've got some new contributors, which is very welcome. We've got some new members who've been contributing. So I'll start with a new member, Mark Oborn. Is Mark here today? No? Well, Mark has sent me an image of the sun on 27th of March, which shows that it's very spotty at the moment. And he took that with a small refractor, 70mm refractor, and a Herschel wedge, which is the thing that goes on the end of the telescope that directs most of the heat and light out of the back of the telescope, and then the image is taken at a right angle to the optical path. And that was taken with a Canon camera, which is astronomically modified. So the sun has been quite active, it's quite spotty, and actually this is one that I took today. So I think this is maybe the record for the closest to the actual meeting that I've ever been able to include an observation in. That was taken at 15:53, which is nearly 5 o'clock today. And I put that in the presentation. That's a sunspot that's on the sun today. There's only one big spot group on the sun today, and that's the one. And that's taken in white light with a white light filter at the front of the telescope, a luminised glass at the front of the telescope, with a 5-inch telescope and a fast frame rate camera, and it's a stack of
video stream that lasted about a minute. Coming on to the planets, now I'd like to crush a bit of a myth here today, because on social media towards the end of March there's a tremendous amount of stuff about a planetary alignment, and lots of posts saying there would be some amazing planetary alignment to see on the 28th of March. And I can prove to you that there was no planetary alignment. This is what the planets were doing, the planets out to Uranus, and you can see the Mercury, Venus, Earth and Mars in the centre there. There's no alignment, they're all higgledy-piggledy. I mean, there's a slight alignment of Jupiter and Mercury, but they were too close to the Sun to see from Britain. There's Mercury, and they were in alignment, but too close to the Sun to see, so there was actually nothing to see. You could argue that there was a slight alignment of Saturn and Mars and Neptune, and Mercury and Venus, but you could have seen from Mars, but even from Mars, all these other planets would have been too close together, too close to the Sun in the sky to see. So there was actually no planetary alignment. So this whole story was a load of nonsense. So one thing to say is that don't get your astronomical information from social media. Get it from a reliable source like WOLAS or the BAA or the SPA, somewhere that they know their stuff. However, what there was a nice grouping on the 24th of March, not the 28th. On the 24th of March there was a grouping of the crescent moon and Venus, and also Uranus was close by in the sky, and here's an image taken by Lee Spencer, a single image taken with a Panasonic camera of the crescent moon and Venus. Lee has been in France, and he said, well, it was poor in France as well. But he managed to get that on the 24th of March, and also on the 24th of March I got that through the clouds, or just before some more clouds rolled in from the west are appearing there. But there's Venus, and there's the crescent moon and the Earth shine, and that was a 1.3 second exposure, single shot, with a Canon DSLR, and Uranus is there as well. It's not obvious, but can you have the lights reduced actually? That would be a good idea.
We believe you.
Yeah, so there it is. Uranus is there. And here's another conjunction. This was sent by Martin Lewis. He took this in January but forgot to send it in before. This is Venus and Saturn. Saturn is now in conjunction with the Sun. It's right the other side of the Sun, and Venus is pulled out much further.
Could you point out Saturn for those who are
Saturn,
not as close as I am?
Yes, Saturn is there. Venus is there. So they were close together on the 22nd of January, and that's a shot with a Canon D500 camera at 55mm focal length. So we've got Mercury in the sky at the moment. We've got both Mercury and Venus in the evening sky at the moment, and I've been taking close-up images of both. And here's one I got yesterday of Mercury, and on the right-hand side you've got a simulated image which is based on the Mercury Messenger space probe results. It's just to see if anything was captured at all. It's hard to say that it was, but you could argue that this bright spot, there is a kind of brighter patch here, maybe in the right kind of place, but it is notoriously difficult to get anything on Mercury. That's another stacked image from a video, and that's taken with a 14-inch celestron telescope and a Barlow lens. I've taken lots of images of Venus recently. I won't bore you with them, but this is just one from yesterday in infrared. In infrared, we normally get a slightly sharper image, but no contrast. UV shows the contrast better in the cloud tops, but the UV image is normally rather blurred, and that's typically what they look like. And you can see these vague markings in the UV. So that's Venus with a 14-inch telescope. And also, early this morning, there was a nice moon up, so I took that one. That's a single shot with a DSLR through my trusty 100mm telescope, with which I've taken a lot of images of the moon over the years. And there's Shikard down there, and there's Tycho with its rays, and there's Aristarchus just coming up on the Terminator. This is an old observation from Martin Lewis, 13th of January 2022, but he's reworked it. He's analysed and reprocessed the videos. He went through his videos and selected the very best of them. He took several on the same night, and previously he tried stacking them all up, but this time he went through them more carefully and determined which were the best videos, and only combined the best ones and the few best frames from the best videos. And he's, by blanking out the planet, he's managed to show a structure around the planet which is in the correct place to be the rings. So there it is, and this is where the ring should be according to a simulation program, SETI, Uranus viewer, and it corresponds. So it looks like Martin has actually captured the ring of Uranus with a 18.5 inch home-built Dobsonian telescope. And so this is from St Albans. So I think this is a first, really. This is a first that this has been done so convincingly with such a small telescope by an amateur astronomer. I think Martin is not here tonight, but well done to him. It's an amazing result, and reanalysis of old data. Kwong Man has been to Indonesia, and here's an exposure with a Canon 100D, 30-second exposure, f2.8. And he sent me this image, and we both had a couple of goes at processing it, various goes, and we found it was possible to process it in very different ways. That was a processing that I did, which makes it a completely different colour, but I think my processing shows the star colours rather nicely. But I haven't attempted to suppress the light pollution so much. Might be a good entry for the astrophotographer of the year, that one, with its scenic quality. Here's another one from Indonesia. This is a different part of the Milky Way. This is the Milky Way was slightly higher in the sky in this one, and this is 2 hours earlier in the sky. And this is 4 exposures stacked for a total of 2 minutes total exposure with a Canon 100D at f2.8. Another, I think he's a new member, John Davies. Is John here today? Here he is, yes. John has been taking images from South Ealing and getting really fantastic results, I think. He's got several different telescopes, and this is a selection of images taken during the early months of 2023. I've arranged them more or less in order in which he took them, and this is taken with a Celestron Edge 9.25 inch SCT at f7, so that would be with a focal reducer, and there's a light pollution filter on there as well, and the camera is an ASI 294MC, and this is a total of about 3 hours exposure, and obviously that is the Whirlpool galaxy in colour, and you've got all these star-forming regions, the red patches in the spiral arms showing up beautifully. The reason it's got so many star-forming regions is it's a double galaxy system. It's interacting with this smaller thing. This is a galaxy that's just gobbling up, and this galaxy is drawing out lots of gas, and it's causing such a lot of tidal disruption that it's causing this wave of star formation. This is all these red hydrogen alpha regions you can see, which are forming the stars. So that's one of John. Here's another of John's images. with the Celestron 9.25, and this is a different optical layer. This is with a hyperstar lens, which is a lens that goes at the top of the telescope and reduces the focal ratio down to f2.2, so it makes it a wide field, fast imaging system. And this has got a filter called an IDAS NBZ UHS filter, so that's a nebula filter, and it's a colour camera SI294MC. It's a guided image, and it's 2 hours 20 minutes exposure on the Flaming Star Nebula in Auriga. And here's a familiar object, the Pleiades, 27th of January, with the Edge 9.25 telescope with the hyperstar lens as well, f2.2, and this is 1 hour or nearly 2 hours exposure. And these are all taken from Ealing, which has a very good astronomical history, incidentally. My predecessor as observations director, Bob Garner, he lived in Ealing, he lived in the borough of Ealing, and great 19th century astrophotographer Andrew Common lived in Ealing as well. So it's got a big heritage. And here's the California Nebula, and this is with a different telescope. This is called a Raptor telescope, which is a 61mm aperture refractor working at f4.9, and the camera is different in this case as well. So this is, I think this is a monochrome camera. Yeah, this is an ASI 2600mm camera, and he's taken images through red, green, and blue filters, and also a hydrogen alpha filter. And the total exposure is 1 hour 30 minutes. The California Nebula, which I forget where that is now. It's in Perseus. Perseus, yes. And here's a very famous object again, the North American Nebula in Cygnus, NGC 7000, again by John from Ealing. And this is taken with the Raptor telescope, and it is he used quite short exposures, 2-minute exposures, so he goes for a lot of 2-minute exposures, and this is a total of 40 minutes exposure in total. And here's the Christmas tree cluster and nebula, which is in Monoceros, and this is the Edge 9.25 telescope, and this is with the hyperstar again. This is taken on the 7th of February, 2 hours 54 minutes exposure. Beautiful colours there. Again, it's an emission, hydrogen alpha emission region, and also a dusty region, molecular clouds, everything in that area. And famous Crab Nebula, that's the Edge 9.25 telescope at prime focus, f10. And that is 2 hours 44 minutes of imaging. That's from the 13th of February, from John in South Ealing. And it would be, I haven't got time to dwell on these too much, but you could spend a long time looking at that. But we have to move on. And here's one he took last night. So quite a few of the images I'm showing tonight were actually taken in the last 24 hours. Here's the Christmas tree again, and this is a monochrome version of it with the 61mm refractor and monochrome camera through a hydrogen alpha filter, and that's 1 hour 15 minutes total last night. So thank you very much for those, John, and welcome to the Society from me. This is by Lee Spencer, and he's processed an image taken by the Icarus Observatory, which is in Spain, I think, some sunny place like that. And this is the Iris Nebula in Cepheus or Cepheus. And this is 80 hours exposure. Did you actually program this image, Lee, or was it one that had already been taken?
No, it's the guy that come from First Light Physics, and he then
he said he's got free data from his observatory in Spain, and I just processed it, tested out bits inside to see how good it was.
It certainly brings out all these dark molecular clouds.
Yeah, it looks better on the computer.
Oh, they often do. It looks not bad on the screen. So that's called NGC 7023. It's the Iris Nebula. And this is from Dewey van der Meer with his Unistellar Equinox telescope. This is a planetary nebula. This is from Uxbridge on the 26th of February. This is the Blue Oyster Nebula, NGC 1501. 24 minutes exposure. Quite a small object. And here's another small object, the Bowtie Nebula, taken 21st of February, 15 minutes exposure with the Equinox telescope, which is only about a 4-inch reflecting telescope with built-in imaging system. And as was mentioned, people are using those telescopes because they actually can connect with a website, so they make citizen science very easy. They make it very easy for you to image, say, a suspected exoplanet system, take images over a period of time, and then upload that to a database. They can, since it's designed, the telescope itself is designed to be connected to the internet, they make that kind of project, that kind of data collection, very easy. And it turns out that even though these are very small telescopes, because there are so many of them around the world now, and because they're all the same, so the data has a certain consistency to it, it's actually very useful to professional astronomers. So actually, these Equinox telescopes are now regarded by some people as the world's largest telescope network. Here's what the moon's doing. It's approaching full at the moment, and the next new moon, 20th of April, and that's soon after that we'll be having the WOLAS trip to the dark sky site in Wales. And then next first quarter moon is 27th of April, which will be a very high moon, which will be very good for observing.
The eclipse you mentioned isn't visible here.
The eclipse is, yes. So the eclipse on the 20th of April, the solar eclipse is total across the Pacific Ocean, and it just clips the northwest corner of Australia. And Sue and Tim have gone to, from WOLAS, have gone to see it. But it's almost entirely over sea. Then there is the corresponding lunar eclipse takes place on the 5th of May at that full moon, but it will only be penumbral, and it will only it will finish shortly after moonrise as seen from here. So effectively it won't be visible from here at all. So sadly we will not see any eclipses, but we will hear about Sue and Tim's experiences at the June meeting. So quite an unusual feature of the sky at the moment is having Mercury and Venus both very well placed in the evening sky. So make the most of that. Nobody so far has sent me any pictures of the two of them together, but they are there. Mercury is getting higher, and it's the 11th of April is the best date. That's when it's at greatest elongation and also highest altitude in the evening sky. And then it will be magnitude -1, it will be 30 degrees high, so you need a good western vantage point or a high window to see it, and it's much lower than Venus. Venus is 29 degrees high, so twice as high, over twice as high, and Venus is magnitude -4, and it's very near the Pleiades at the moment. And Uranus is there as well, but you won't see Uranus because it's too faint in the twilight. The moon will pass Mercury on the 21st, and the moon will be only 1 day old, but it will be a very difficult observation to see that moon, quite a challenge. So see if you can see the moon on 21st of April and catch it near to Mercury. Again, Uranus is close by, but that won't be seen. By the 23rd of April, there's a crescent moon only 2 degrees above Venus, By that time, Mercury is receding again. Mercury is only 7 degrees high, 30 minutes after sunset by that time. So the window for observing Mercury is really about a couple of weeks, but this is the best opportunity to see it this year, whereas Venus will go on getting a good view of Venus throughout May and into June. Mars is still dominating the evening sky, and the Moon is near Mars on the 25th of April, and this diagram is drawn for 2130, which is just at the end of nautical twilight, just getting quite dark, and the pair will be 40 degrees high then, Moon and Mars. Mars is well past its best, it's down to magnitude 1 now. You will still have some chance of seeing details in a telescope, but it's getting difficult to see details on Mars with a telescope now. And Mars will be setting about 2:30 a.m. and Venus will be setting at midnight. There's asteroid number 7, Iris, at opposition on the 30th of April, but not very high in the sky, only 18 degrees high in the sky, and its magnitude 9.6, so not an easy target, but that's a low number asteroid that is coming to opposition. It will just look like a star-like point. If you can find it, it will be identifiable by its motion from night to night, and it is in the Libra area. There are some meteors in April. There are the Lyrids, which are around the end of the month, and this is a very favourable month for them, very good for the Moon, and the peak of them is very precise. It's 5 hours on the 23rd of April. So early morning on the 23rd of April, that's the peak for the Lyrids. It's 15 meteors an hour is the theoretical maximum that you could see. And the Eta Aquarids also contribute a few meteors at this time of year, although the radiant is too far south to be well seen from the UK. But they produce quite a lot of meteors, but a lot of them are below our horizon. But you may see some in the south of the sky. I did see a meteor last night, actually, which is very unusual for me. That's all to say, except next WOLAS meeting is due to the coronation, is the 3rd Monday in the month, so we've now got a 5-week gap. And actually I won't be there because I've got a meeting with another organisation that night, but I will collect your observations for this month and I will then send them to Robin to show. So that's all from me.
Thank you very much, David. And thanks also to those members who contributed your photographs. It was nice to see so many. I thought that we'd maybe just have 1 or 2, but there were plenty, and they were all super ones as well. As David said, our next meeting is on the 15th of May, and it will be Steve Tonkin coming down from Fordingbridge Way, and he'll be talking about 2 eyes are better than 1. In other words, using binoculars. And there's an amazing amount of stuff that you can see, not just the planets and the bright clusters, but also quite a few galaxies as well. So that's on the 15th of May, the week after the coronation. Now, our treasurer, Martin Lewis, isn't here tonight. He's getting over a knee operation. But if there's anybody who needs to pay up, your subscriptions became due, £12 for most people, on the 1st of April. And if anybody hasn't paid and they wish to foist money on me, then I will take it on behalf of Martin and send it on. And so thank you very much again to Giovanna for her wonderful talk. Stuart, you have got a...
Yeah, if you didn't manage to sign in on your way in, could you do so on your way out, please?
Yes, please sign out if you didn't sign in. Thank you very much and good night.